Hi everyone, I'm Emily,
And I'm Andrew.
and we're going to show you the science and math behind our meditation tracker. To start, we need to think about what meditation is. Scientifically, meditation is a relaxed state where we slow down our heart rates, calm our mind, and follow repetitive breathing patterns. There are many ways to measure someone's mental state, but to ensure that someone is truly meditating, the most reliable source of information is from brainwaves. Every human creates brainwaves, and depending on how they're thinking, the types of brainwaves they create differ. For example, if I'm concentrating really hard, doing some math, or holding a conversation with someone, I'm likely to generate a lot of gamma waves. These are brainwaves that appear in scenarios that are where there's high perception, learning, and problem solving. However, if I were to close my eyes and relax my thoughts, those gamma waves would disappear, and the most prominent waves would be theta waves, which represent creativity, insight, reduced consciousness, or dreaming. The way that we distinguish between these waves is based off of frequency. Each wave is represented by a range of frequencies that the brainwaves express. The diagram here shows the different ranges of frequencies that correlate to the different types of brainwaves and associated mental states. So there's gamma, beta, alpha, theta, and delta waves. Go.
Due to the fact that we can identify different mental states by the frequencies that brainwaves express, we can extract a lot of meaningful information from this type of data. The first challenge is collecting the brainwave data. In most cases, very expensive equipment is needed to collect brainwave data. However, Professor Sam Mahalka was very kind and lent us a Muse headset, which has 4 electrodes that go in your forehead and collects data and sends it to a mobile device. With this device, we were able to collect a set of brainwave data to test our mental state. To begin this, we took a data set of me with my eyes open, counting backwards from 100 in units of 7, then I closed my eyes and relaxed my thoughts. This is what the data set looked like. So as you can see, by looking at the raw data alone, it's very hard to get any information about my mental state. So we're going to have to add a filter to this data. There are many types of filters that can be used to extract certain pieces of information from data, such as the high-pass filter, low-pass filter, the Gaussian filter, bandpass, or a comb filter. But the filter that we'll find most useful for this data set is called the moving average filter. The moving average filter is very useful for this context because it allows us to reduce the noise of the data, but it still lets us analyze all the frequencies present in the signal. Here I'll explain how the moving average filter works. So say we have this data set here, where we have an X series along the X axis, and then some other plane Y. And from this data you can see that there's no real trend, and the data points vary from each X value. We're going to perform a smoothing operation here. So say we take this point here, X of 5, and we apply a filter on it, giving us some value for Y of 5. So the way the moving average filter works is we have Y of 5 equals, this is for a 3-point moving average filter. So we'll have X of 4 plus X of 5 plus X of 6 over 3. And this will give us a point for Y that takes all of these 3 points into account and gives us another point that's probably around here, which is the moving average, so it's the average of these 3 points. In the previous example, we did a 3-point moving average filter. Now let's expand that to an n-point moving average filter. So we have our output signal y of I. So for the point I, and this is analyzed on the point xi, so we're going to take n, which is the number of points we want to do the average across, and do the sum from negative n over 2 all the way to n over 2 divided by n, and that will give us an n-point moving average filter.
Good. So Andrew just went over the mathematics behind a moving average filter, but this is what happens when we actually apply it to a noisy brainwave. So let's break this down a little bit. Right here in the beginning, you can see that this is where Andrew was thinking really hard because we have a lot of noise, it's going up and down a lot, and this exhibits gamma waves. Right here is where we can see where Andrew blinked, this large peak right here, because the Muse picks up on any kind of movement, and that creates a large noise in your signal. Then down here at the end is where it gets really interesting. This is where Andrew's relaxed, and he's closed his eyes, and he's starting to try to get into that meditative state. And so here you can see it's a little more smooth, and right here you can actually see a repeated signal happen.
So now that we've proven that we can identify types of brainwaves from a signal, we can use this information to create the tracking part of our project. We want to be able to map your mental state over a fairly large period of time. In order to do this, we're going to break up the signal into smaller parts and perform what's called Fourier analysis on each segment. For this example, we split up the signal into 5 equally spaced sections and performed Fourier analysis on each of the sections. At the core of Fourier analysis is something called the Fourier transform. This equation here represents the mathematical operation that is the Fourier transform. Basically, what the Fourier transform allows us to do is convert a signal from the time domain to the frequency domain. And this means that if we plot the Fourier transform of a signal, there will be peaks where each peak represents a frequency that is present in the signal. So in this graph, we can see the actual result of the Fourier transform. So we have a sine wave up here, which is operating at 0.9 hertz. And then if we take the Fourier transform, it gives us this plot here, which is reflected on both sides of the zero. But essentially, we can ignore this half and just look here, and we see that there's a distinct peak right at 0.9 hertz that corresponds to the frequency of the sine wave above.
So our next step is to run Fourier analysis on each of our 5 different segments that Andrew mentioned earlier. So when we do this, we only take or care about the positive half of the Fourier analysis because that's what we run peak detection on. So you can see these different little triangles, and those show a different peak that we detected. So after peak detection, we take our peaks and we put them into our algorithm. How that works is we want to match our peaks to what wave they are, what brainwave they are. And then from there, we give them a numerical value. So we have a scale from 1 to 4, 1 being most relaxed, 4 being the most active. So we have gamma waves up at the top, and then we have theta waves at the bottom, with beta and alpha being in between. Gamma get a score of 4, and theta get a score of 1. So, for example, out of peak detection, I get that we have a reading of 28 hertz and one at 44. 28 is going to be beta, and 44 is going to be gamma. So the 28 gets a value of 3, the 44 gets a value of 4. Then we average these two, right? So we add the 3 and the 4, and we divide by the total number of peaks. So we get an overall section reading of 3.5. We do this to each section that happens within a session, and then we develop this graph for the user, which shows them how their meditation was. The most important part of this is this red line right here, which shows you that this is like our meditative state indicator. So above this is you're really active, and below this is you're relaxed. The further away you get from this red line, the more relaxed you were, the better your meditation is. And then once you cross, you know you've gotten out of that meditative state, but you can see that you're able to bring your brain back down into a relaxed state, which is what is really important.